and also another two equations, psi 2 equals psi 3 at x equals L, psi 2 prime equals psi 3 prime at x equals L. So now I have four equations, and if I assume that I have thrown a particle only from the left traveling towards the right, okay. Again, remember, this is a one-dimensional case. It's only movement along the x direction, nothing more. So if I've thrown a particle traveling from left to right, then I'll have some reflected part, some transmitted part, or tunneled part, whatever. Sine theta, e to the power ikx plus b e to the power minus ikx. Yes? That would be psi 1. I can, sorry? Differential. D psi by dx is psi 1 prime. Right? Then I have psi 2, which is you see e to the power minus k2x. But in general, I should also write d e to the power plus k2x, right? Because there is a finite probability that some of the wave would reflect back at this border at x equals n. Though whatever happens, it will come down. It will come down to a large extent in the intensity when it comes back to x equals 0. Okay? But in general, I should consider that. Just a moment. Psi 3 then again would be equal to do not confuse this for energy. E to the power ikx, ignoring this one, because I do not throw anything from the right. Okay, so I ignored the last one. Yeah, somebody had a question. No, the reflected would be also of the form e to the power minus kx. No iota. See, again, the thing is that your potential is larger than energy, then the value of k comes out to be imaginary. No. Look at this. Where did we do? Yeah. So if the value of V is greater than the energy of the wave, okay, then this K2 comes out to be an imaginary quantity. Always. No, that's also free. The energy doesn't change. I am not changing the energy of the wave. Still, the energy is the same. No? For the energy does not depend on the position. The energy of this complete wave is one energy. Right? Okay, so I have now 5 unknowns, 4 equations. I can always write my transmission coefficient or reflection coefficient, right? B in terms of A or C in terms of A. We will not attempt to solve that. Okay, I tried once. It took me half a day, and then I thought it's best not to do that and straight away write the expression. So the transmission coefficient is essentially approximated. Okay, I will not even write the exact expression is also given over there. The approximated expression is 16 epsilon 1 minus epsilon e to the power minus 2 k2L, where epsilon is nothing but E by V naught. So if, and let's see what the gross features are. Okay, V naught is in the denominator. The higher V naught, the smaller the value of T. Which means that if I have a very high potential barrier, I will not be able to observe the wave on the other side. L is e to the power minus L. Again, if I have a wide barrier, then the wave function will just decay within the barrier. You will not be able to observe it. Also, there is something in K2, that is root 2 ME. So M is another constant over there. So if I have larger masses, again it goes into the denominator, right? So if I have larger masses, they will not be able to tunnel through. So this works only at small masses, small widths, small heights. Okay, and it works so beautifully that you can actually see the particle on the other side of the barrier. And there's an instrument that is built on this principle which is known as the STM. Okay, the scanning tunneling microscope. So think of this as an atom surface. Yeah. So I have, think of these round spheres of atoms placed together. And then what you do is you can bring a tip which is very close to this surface, not in contact, okay, very close, and then you start applying a potential between them. So that is, you are providing some energy to the electron, right? And the electron jumps from the surface to the tip, or the other way around, whichever, right? Now all I have to do is maintain a constant height, and the current that I'll observe would depend on this distance, right? If it is a small distance, it's a small width of the barrier. If it's a large distance, it's a large width of this barrier. Okay, this is a barrier. It's not in touch, so there's a barrier. The current normally cannot flow. It's an insulating barrier, right? Or rather, not completely insulating, but it has some resistivity. So that resistivity essentially denotes the height of the barrier, and the distance from the tip denotes the width. So you have very advanced piezo transducers which can control the height of the tip and the movement that it makes along the x or z. So x or y is the plane and z is the height. So everything can be controlled very accurately, and you can actually, I think you can get resolutions less than an angstrom with these kind of techniques. So in one of the notes, I think it was discovered in 1980 or 82 by IBM at Switzerland. So this image, which has not come out very nicely, my printer had gone back, but it's an image of cesium atoms lying on top of gallium arsenide substrate. Okay, have I posted these online? If somebody says yes, then yes. Okay. So I think I did something yesterday evening, but I forgot. Also, a lot of chemistry is based on tunneling. You know, the way the electron transfer reactions take place, that depends on the tunneling barrier. The way, the very common example that everybody gives is the flip-flop, the umbrella inversion of ammonia. That is because of tunneling. Tunneling of hydrogen atoms up and down, although there is a barrier. Okay, so all these barrier processes that have barriers, and you do not have enough energy, most of the energy comes from heat, thermal energy. If you are at even low temperatures, still some of these molecules go over to the other side, and that is because of tunneling. So you normally have these kind of potential barriers between the reactants and the products, and even at low temperatures. So if you do not have energy, this much energy, you have something like this, only this much energy available. Still, if something gets converted, that's because of tunneling. The DNA base pairing, the way it replicates, that's another example of hydrogen being tunneled across these bases. So all those things, there's a lot of things that happens because of electron atom tunneling. So small atoms would tunnel much better than large ones. Okay. So that's all I wanted to tell you. And